My name is Michael Gonzalez, and my project is the study of pneumatic artificial muscles and one-way spring-return pneumatic cylinders. My project is important because it offers a working prosthetic arm without breaking your bank. It also resurfaces the McKibben muscle, which we do not see used in modern robotics. This is probably because of its low range of motion. The problem I saw was that prosthetic arms were just too expensive, coming in at anywhere from $5,000 to $100,000. So I wanted to make a strong and flexible prosthetic arm at just a fraction of the regular price. My engineering goals were to make the arms move, to make the arms mobile, to make a relatively cheap prosthetic arm, to create a code that allowed an SCMG sensor to communicate with an Arduino and a Duin 12V micropump, to find the best PSI to operate a pneumatic cylinder at, and to find the best length to make a pneumatic muscle. The two lifting mechanisms I used were one-way spring-return pneumatic cylinders and the McKibben muscle. To test which one lifted more, I made a model arm with the measurements of my arm and attached each lifting mechanism to said arm. I then added compressed air to each arm with weight at the end where the hand would be. I then recorded the weight that each model was able to lift and compared the results. While the pneumatic cylinder arm was able to move without any weight attached, as soon as I added a weighted bucket, it wasn't able to move. This is probably because it was intended to hold up car hoods, not make prosthetic arms. Therefore, it was able to lift 0 grams. All the pneumatic muscles were not able to lift or curl the arm in any way when they were attached. So I took them off and tested them on their own. The 25.4 centimeter pneumatic muscle was able to lift 12,247 grams. The 30.48 centimeter pneumatic muscle was able to lift 10,886.2 grams. And the 35.56 centimeter pneumatic muscle was able to lift 13,154.2 grams. While the pneumatic cylinder arm failed when it came to lifting weights, it soared when it came to range of motion. The pneumatic cylinder arm had a range of motion of 53.34 centimeters. The 35.56 centimeter pneumatic muscle had a range of motion of 5.08 centimeters. The 30.48 centimeter pneumatic muscle had a range of motion of 3.81 centimeters, and the 25.4 centimeter pneumatic muscle had a range of motion of 2.54 centimeters. An error that might have affected the results is the pneumatic cylinder being so weak. Maybe if I used a higher grade pneumatic cylinder, it would be able to surpass the pneumatic muscle. Another error is me taking off the pneumatic muscle. Maybe the angle in which the weight was pulling on the pneumatic muscle affected the amount of weight it was able to lift. So the pneumatic muscle wasn't able to lift any weight on the arm, which ends in a fail. The results show that the pneumatic muscle was able to lift more than the pneumatic cylinder. One limitation I had was lack of time. Unfortunately, some of the materials came in very late, so I was not able to incorporate them into my project. These materials consisted of the Arduino and the MyAware SCMG sensor. If I were to be able to use these in my project, it would take the project to a whole new level. Basically, whenever I flexed my bicep, the arm would curl. However, because these got in very late, I was not able to do this. An assumption I had was that the Duin 12V micropump would be able to run on a 12-volt Duracell battery. However, I need special adapters to operate the Duin 12V micropump. Therefore, I was not able to use this either. However, my designated supervisor had a backup air compressor, and we used that instead. If I were to continue working on this project, I would incorporate the code into my project. I would come up with a new design for my pneumatic artificial muscle arm, and I would use a higher grade pneumatic cylinder.